remind everybody to mute their cell phones or turn them off so they don't go off in the middle and then we point at you. Our 2018 calendar has one opening left in it. We're starting on 2019. We got a great suggestion from Earhart. Other people who have suggestions about programs you might like to see the year after next, let us know and we'll pursue them. So it's wonderful to introduce Dr. Samuel Singer. Samuel has done, this will be his third talk for us, so I feel like I hardly even need to do an intro. But Sam grew up exploring the high desert in Yerington, Nevada, which I had to look up. It's about 50 miles east of Lake Tahoe. He got his BA in physics and astronomy from Hampshire College, and this is where he discovered his love for outdoor education. He earned a master's in science education, environment and natural resources from the Teton Science School of the University of Wyoming. Over the past decade, Sam has worked as an outdoor educator and wilderness guide in Wyoming, across the country. He got his PhD in science education from the University of Wyoming, and his dissertation was about the focus on the spirituality in outdoor environmental education. Sam's an accomplished astronomy educator and amateur astronomer. He is the founder and executive director of Wyoming Stargazing, which is a wonderful local nonprofit. If there's an astronomical event, Sam will have the scopes set up and you can check it out. I've seen some great stuff. They have programs all year long, and without further ado, please join me in welcoming Dr. Samuel Singer.
Well, thanks so much. Really appreciate you having me here tonight.
He must.
Over the next hour, I'm hopefully going to convince you. Can you hear back there in the back?
No.
Oh. Uh-oh. You have a dead battery?
Here.
Yeah, dead battery. Now it's back on. Can you just switch it out?
Switch it out. That one's last. Excuse me. It works. All right, how's that?
Good.
Great, huh? Good and back?
Yep.
Good. Yeah.
Okay. Well, over the next hour beginning now, I'm hopefully going to convince you that the Hubble Space Telescope is probably one of the most incredible scientific instruments ever built. And that certainly it represents the greatest advancement in astronomy since Galileo first used a telescope to look at the night sky in 1610. So we're going to start with some background on the instrument itself. Then I'd like to share some of what I think are the coolest discoveries from the Hubble Space Telescope and some of its most profound accomplishments. And then I want to share a little bit about some of the new up-and-coming big space-based and ground-based telescopes that are either in production now or will come online in the next decade. There's a lot of really cool stuff that's happening in the field of astronomy. Might have to be closer. Oh, there we go. So, April 24th, 1990, the Hubble Space Telescope got launched on top of, or inside, Space Shuttle Discovery. And as you probably know, the telescope, the Hubble Space Telescope, is named after the famous American astronomer Edwin Hubble, who was the very first person to identify galaxies outside of our own, before all those big spiral fuzzy spots out there were just known as spiral nebulae. And there was really no one who understood that they actually lay outside the Milky Way galaxy. It was assumed that they were actually inside the Milky Way. But Hubble was the first to actually produce scientific data that showed that they were outside the Milky Way. And so because of that accomplishment, he has probably the most profound telescope ever named after him. So the mirror of the Hubble Space Telescope is roughly 7 feet in diameter. Really cool reflection there of that guy looking into the mirror. And the telescope in total is about 13 meters long, so roughly the size of a school bus. That's a pretty hefty instrument. And since 1990, there have been about 1.2 million observations made with the Hubble Space Telescope. And from those observations, over 14,000 scientific papers have been published. And still more all the time. And so if you look at all the data over that time scale, it adds up to about 120 terabytes of data. And the data mining that's going on right now for the archive actually produces another 10 terabytes a year. And I want you to remember that figure, 10 terabytes a year. There'll be a really cool number to compare to the amount of data that the new telescopes being built now are going to be producing. So 10 terabytes per year is what's currently being produced with the Hubble Space Telescope.
Are you going to explain to us the difference between general observer and archival?
Yeah, so the only difference is, good question. The only difference is that the general observer, that's when somebody writes a grant and gets time on the Hubble Space Telescope. Whereas archive is actually looking at data that's already been collected in other research proposals that's available to the public. So anyone can get Hubble data and do research with it once it's been collected. Great question, thank you. So I want to show you this animation. Thought it was going to play by itself. I'm going to have to click a button here. And it just shows how the Hubble Space Telescope moves around the Earth. And while we're watching it, I'll give you a couple figures just about its motion. It's going to work for us the first time. Ah, isn't that nice? So, since 1990, the Hubble Space Telescope has traveled about 3 billion miles around the Earth in low Earth orbit, about 340 miles above the Earth. And it moves at about 17,000 miles an hour. I'll play it through one more time. And one of the incredible things about it is that it doesn't have any thrusters to point in any specific direction. It uses Newton's third law of motion, equal and opposite reactions. By spinning its wheels in one direction, it creates motion in the opposite direction. And so to turn a full 90 degrees to point at an object takes it about 15 minutes. So it's a real slow motion, but it's just Newton's third law. And its pointing accuracy, let's see, I think I have to get out of this now. Let's get back to the slideshow. There we go. There we are. And its pointing accuracy is 0.007 arc seconds. And what that's like is, it's like pointing to a dime with a laser 200 miles away. So if somebody was holding a dime in Salt Lake City, the Hubble Space Telescope could point directly at that dime without any problem at all. And in terms of its resolving power, it's about 0.05 arc seconds. And what that is like looking at a firefly in Tokyo from your home in Maryland. So incredible, incredible precision. The weight of the Hubble Space Telescope, when it was first launched, was about 24,000 pounds, the equivalent of 2 African elephants. So there they are. But that was just the initial weight. Since it's been launched, there have been 4 different service missions, and each time additional instrumentation has been added. And so now the total weight is up to about 27,000 pounds, about 3,000 pounds more than what it was originally. Before I tell you about this image, just one more interesting thing about the telescope itself, in that it runs completely on solar energy. And most of the solar energy captured by its solar panels gets directly converted to electricity and not stored in batteries. There is some solar energy that is stored in batteries, but that's only used when the telescope actually passes through the shadow of the Earth, when it's not getting any direct sun. But the rest of the time, it just uses direct solar energy hitting the photovoltaic panels, which gets converted directly into electricity. So I want to talk to you a little bit about the specific instrumentation on the Hubble Space Telescope, but I'm not going to show you any pictures of the instrumentation. I'll show you one, actually. And that's because the pictures taken by those instruments are way more interesting than the instruments themselves. So I'll spare you looking at these black boxes and just show you the amazing beauty of the images that they've produced. So there are 6 different instruments that I'm going to talk about. The first 2 are different sets of camera arrays. So the first one is the wide field camera. Wide field camera 3, to be precise. And this camera can see not only in the visible light, but also in the ultraviolet and near infrared, but not simultaneously. It has different sensors for those 3 different wavelengths. And the resolution and the field of view of this camera is the greatest compared to all the other instruments on the Hubble Space Telescope. And so if you have seen any of the truly amazing visible light images from the Hubble Space Telescope, those are images that were probably taken with the wide field camera. And not only does it take incredible images, but it's also used to study dark energy. It's used to look at individual galaxies, as well as looking at planets in our own solar system. So it's really versatile. This picture here is of the Horsehead Nebula. And the Horsehead Nebula is what's called a dark nebula. Dark because the light that's emanating from the nebula is blocked in the visible light spectrum. And it's just blocked by huge clouds of dust that lay on the outside of the nebula. But with this camera, with the wide field camera, we can look in the near infrared and basically peer through the dust and see all the details in the inner part of the nebula itself. So these nebula are basically stellar nurseries. They're the place where new stars are forming from collapsing gas and dust inside the nebula that's superheated because of its compression. And as a side note, which is maybe more interesting than the shape of this nebula, is that very recently, just in the last few years, some ground-based radio telescopes have discovered chemical compounds in the Horsehead Nebula that don't exist on Earth. It's a chemical compound that exists only in space. And there are actually several other chemicals that have been found in other such nebulae that appear only to exist in space. They're highly unstable, And they can't exist on Earth, even though they have been synthesized in a lab for more than a split second. And then they fall apart. But in space, they're stable. And so it turns out there's a whole new array of chemical compounds that are just floating around out there that we're just discovering in the last few years. So the other camera that I want to talk to you about is called the Advanced Camera for Surveys. And the Advanced Camera for Surveys also sees in the visible light, as well as in the ultraviolet, and not in the near infrared, like the wide field camera. This camera is also used to peer into big swaths of galaxies. And so it studies the structure of galaxies and is much more apt to looking at really large areas of the night sky, whereas the wide field camera can do a little bit better on smaller areas. So this picture here is probably one of the most famous pictures of deep space that the Hubble Space Telescope has ever taken. This is what's called the Hubble Ultra Deep Field. And when it was taken in 2005, it was by far the deepest we had ever seen into the universe. And what you're looking at here is a field of view that's roughly the size of the full moon. And it contains about 10,000 galaxies. Each point of light is an entire galaxy, with a couple exceptions. This one right here, and this one right here are stars, that's right. And then down at the bottom there. Yeah, so those are foreground stars in the Milky Way galaxy that the Hubble Space Telescope is peering through to see these other galaxies. So 10,000 galaxies in this tiny little piece of the sky, each of them on average with 200 billion stars. And so this is one of the ways that Hubble has really changed the way we think about the universe. The sheer number of galaxies that we now know to exist is in part due to pictures like this taken with the Hubble Space Telescope. Oh, great question. I wanted to mention that. There are some galaxies in this picture. For instance, this little red guy right here. And where's another good one? This one up here. And yeah, exactly, the deep red-shifted ones. Yeah, a couple of purple ones, and the really faint red ones, unfortunately, aren't showing up on the screen right here. The resolution's not good enough. But there are some galaxies that are about 12.5 billion light years away that showed up in this image. More recently, an infrared version of this image was taken. And galaxies just around 13 billion light years away showed up. And then there have been a few other such pictures taken in different parts of the sky that have also shown galaxies roughly 13 billion light years away. So almost to the edge of the visible universe. So in addition to the two sets of cameras, there are also two spectrographs on the Hubble Space Telescope. And I did just want to show you at least one picture of instrumentation here. And so this one is the Cosmic Origins Spectrograph. COS is the abbreviation for that one. One of the newer instruments installed in Hubble. And this one sees exclusively in the ultraviolet. And it increased the sensitivity that the Hubble Space Telescope had about 70 times when it was installed. The other spectrograph, called the Space Telescope Imaging Spectrograph, can see not only in the ultraviolet, but also visible and infrared. And the other one is known for its ability to hunt black holes. It's really good at finding black holes. While this one works best on stars and quasars, which we'll get to a little bit later. But just to explain what a spectrograph is, A spectrograph is an instrument that works somewhat like a prism and separates the light from the source that it's looking at into its constituent wavelengths. And so, instead of seeing an image like this, you get something like this. The light is spread out over the color spectrum. And there are a few different types of spectrum here that I'll explain briefly. The top is a continuous spectrum. And that's when you look at a light source that is such as a star, and the light source isn't blocked by anything. There's nothing obscuring it. The absorption spectrum would be from a source where the light is being blocked, maybe by a cloud of gas. And so some of the wavelengths of light get absorbed by that cloud of gas, depending on the elements present in that cloud of gas. And then down at the bottom is an emission spectrum, which would be looking at a cloud of gas that's illuminated itself. The light actually coming from a diffuse cloud, as opposed to a point source. That's kind of the basics in spectroscopy. And we can learn a lot by looking at these spectra, because each individual star, each galaxy, basically has a spectral fingerprint that we can use to identify it. And it tells us the temperature of the object, chemical composition. It can tell us how fast the object is moving by looking at how those lines get shifted in one direction or the other. So there's a ton of information locked away in these spectra. The last instrument that I wanted to mention is a spectrometer. Now, it works similar to a spectrograph, but instead of producing those nice spectra, what it does is it looks at just the light that gets absorbed by gas clouds. And so it basically allows us to peer into really, really bright objects that are obscured by gas to actually see into those objects. So here's one example of a visible light image on the left. And what that spectrometer can produce of the core of that image. You can see way more detail there that's otherwise obscured. So now I want to talk about some of what I think are the coolest discoveries over the past 27 years with the Hubble Space Telescope. And these next few images I'm going to show you are not real images. These are all artists' impressions of what it would actually look like, because they're just too far away to get actual photographs of. So this is a picture of what's called a hot Jupiter. Hot Jupiter is a planet that is orbiting around another star. The star could be roughly the same size as the sun, or smaller or larger, but the planet is roughly the size of Jupiter. However, it's orbiting at a distance around that star more close to where Mercury would orbit around our sun. So it's really, really hot, thus the name Hot Jupiters. Well, the Hubble Space Telescope collected the first data that actually showed one of these hot Jupiters vaporizing its atmosphere out into space. So we can actually see, figuratively see, a planet with an atmosphere, and the atmosphere is it's being superheated because it's so close to its parent star that it's literally just wafting out into space, almost creating a comet's tail around this planet. So Hubble was the first telescope to produce any data of cometary-like tails around planets moving around other stars. So this is an artist representation of a protoplanetary object, a big chunk of rock, orbiting around a white dwarf star. And through data similar to this, the Hubble Space Telescope has allowed us to understand that there are probably planets forming around all kinds of different stars, not just stars like our sun. And it seems to be the norm as opposed to the exception. There's really good evidence collected by the Hubble Space Telescope that all different types of stars can potentially form planetary systems like our own. And in several of these cases, water has been observed. So we know of several stars that have chunks of debris around them that also have water and these big accretion disks moving around them. So data from Hubble was the first to confirm that all different types of stars can form planets. So this is an interesting one here. This is our representation of what a quasar might look like from up close. Oh no, excuse me. This is something different. This is a primordial galaxy with quasar-like jets coming out of it. Maybe a quasar. But the idea was that these incredibly powerful jets were heating the intergalactic medium. And that had a huge effect on the amount of star formation that could happen in the early universe. We're talking about 11 billion years ago. The first galaxies are forming, and these huge, powerful jets are moving out from the largest galaxies and probably stunting the growth of smaller galaxies by prohibiting star formation in those smaller galaxies. And again, it was Hubble data that allowed us to understand that. This was another fascinating discovery a little more recently, also involving quasars. So let me just say a little bit about quasars. The word quasar stands for quasi-stellar object, because when they were first identified, nobody had any idea what they were. They're objects that shine with the brightness of entire galaxies, but they look like they're roughly the size of stars. And so by looking at the light through a few of these quasars, we've actually been able to see that there is this enormous halo of material that exists far beyond the edge of what we can visibly see around galaxies. This enormous halo of hydrogen and sometimes helium gas. And it's believed that this huge halo of hydrogen and helium gas is constantly being recycled in and out of the galaxy. And it's what propels the process of star formation. And so what Hubble has showed us is that basically galaxies are the ultimate recyclers. That they can continuously expel hydrogen and helium gas and bring it back in to continuously form stars over billions and billions of years. Hubble also solved a long-standing mystery about this long stream of material here, down here, and then up there as well. For over 40 years, astronomers couldn't figure out why there was this huge stream of material down below the disk of the galaxy and then up above it a little bit. Through observations of the Hubble Space Telescope, it was realized that that material actually got stripped away from the two satellite galaxies that move around the Milky Way galaxy, the large and the small Magellanic Clouds. And so now, these streams of material are called the Magellanic Streams. And it's believed that just through tidal interactions, the Milky Way was able to strip away large amounts of material from our two satellite galaxies to create those two swaths of debris out there. So there were a total of 4 service missions to the Hubble Space Telescope, bringing new equipment up, fixing old equipment, fixing sensors, batteries, that kind of thing. And the final service mission took place in 2009. That was done by Space Shuttle Atlantis. And if you remember, that was just after Space Shuttle Columbia was destroyed. So it was a big deal to do this last service mission. But that's it. There's no way right now to repair anything on the Hubble Space Telescope. So if something breaks, it's dead in the water. You may have read about the Kepler Space Telescope. Part of its guided system, one of the gyroscopes broke. and so it can no longer be pointed. So if something like that were to happen on the Hubble Space Telescope, it would have the same fate as Kepler. We just couldn't use it anymore. But I had the great pleasure of meeting this gentleman this summer, who was the last astronaut to do a service mission on the Hubble Space Telescope. So you can really see the whole size of the Hubble Space Telescope here. It's pretty amazing compared to... Yeah, right? That's probably, or probably bigger than that. It's probably like a size 20 boot sticking out of there. So it's a huge instrument. And this gentleman is not a small individual. He's known as the world's largest astronaut. He stands about 6'4". He's a big guy. Scott Altman is his name. And he joined us for our Eclipse party this summer up on the top of Snow King. And so he was up there in 2009 doing the last service mission. So he has the honor of being not only the last person to touch and to fix the Hubble Space Telescope, but also to break it. I don't know if any of you have seen the incredible IMAX movie about the repair work on the Hubble Space Telescope. Scott's featured in that movie, and there's a scene where the astronaut has to break off a handle because it's jammed and they can't get a compartment open. That was Scott. So he got to touch the Hubble Space Telescope, fix it, and break it after anybody else. And so you can see, I think it's, I guess, part of the one side of Hubble out the window there. And Scott also sent me this next picture, which I think is maybe the coolest picture in this whole slideshow. So what you're looking at here is you're inside Space Shuttle Atlantis. This is the Hubble Space Telescope out the window. And this is one of Galileo's telescopes. Right? Yeah. Yeah, when he sent me that picture, I was so excited. So yeah, I mean, you're looking at 400 years of the evolution of the telescope right there. The very first telescope that was pointed up at the sky, and the most profound telescope that we've ever pointed at the sky. So yeah, I love looking at that image. I think it's just too cool. So this one's not bad either. This is kind of cool. This image kind of shows you the kind of work that the Hubble Space Telescope is doing now. It currently has two focal points for research through the year 2020. One is exosolar planet research, looking for planets orbiting around other stars in the Milky Way galaxy. Pictures of that research are not really exciting. They're just spectra, like I showed you before. The other area of research that Hubble is looking at, working on right now, have very exciting pictures associated with it, and that's called frontier fields. So frontier fields, that project is focused on looking at the most distant objects that we could possibly see. And the way that Hubble is achieving that is by looking for gravitational lenses. And so this is an awesome example of a gravitational lens. So what you're seeing here is a huge cluster of galaxies, big elliptical galaxies, all these fuzzy spots here. And this is foreground, all these big elliptical galaxies. That's much closer than anything else. And then you're seeing all these really weirdly shaped, skewed objects. And those are galaxies behind that cluster that's closer to us. And their light is being bent around the cluster because of the huge gravitational effect on space that this cluster has. So it's basically working like a giant magnifying glass and refracting light around its edges. And so those galaxies that you're seeing that are all skewed are much farther away than any telescope can actually see without the help of that gravitational lens. The gravitational lens also magnifies the light, and so we can see stuff from much, much farther away behind those gravitational lenses. This is one such example of what Hubble's looking at right now. And what's that?
Amazing.
Oh, yeah. Yeah, it really is. A black hole can do something similar. A black hole can also work as a gravitational lens. But this is just a big galaxy cluster. So, if all those cool discoveries and cutting-edge research weren't enough, there's also a long list of accomplishments that have really changed the field of astronomy that the Hubble Space Telescope is responsible for. And I want to share some of those with you as well. So the first is the age of the universe. So before the Hubble Space Telescope, the age of the universe had a pretty big range to it. We thought it was, somewhere between 10 billion to 15 billion years old. I mean, it's not a bad range, but still pretty large error bars there. The Hubble Space Telescope changed all that. With observations with the Hubble Space Telescope, that figure was narrowed down to 13.7 billion years old. So it took a wide range and brought it to a number with a decimal point, which is pretty amazing. And it did that in 3 different ways. It did that by looking at very, very old stars in globular clusters, clusters, really tightly packed clusters of stars that hang out in the upper and lower halos of spiral galaxies. It also looked at what are called type 1a supernovae, which I'll get to a little bit later. And most importantly, it looked at a specific type of star called a Cepheid variable. So Cepheid variables are stars that are unstable. They pulsate. And it turns out that the rate of pulsation is directly related to how luminous, how bright the star actually is. And it turns out that the very brightest stars have a longer period of pulsation. They pulsate more slowly, whereas the fainter stars pulsate more rapidly. And so if you can identify some of these stars at distances that you already know, such as inside the Milky Way galaxy, and then you look at distant galaxies and you identify Cepheid variable stars, measure their apparent brightness, measure their period of pulsation. You can then use their intrinsic brightness, the brightness that you know they have to be based on their rate of pulsation, to figure out the distance. You compare how bright they look to how bright they actually are. It's just like trying to measure the distance of a car from you by looking at the brightness of its headlights, but over millions of light years. And so the Hubble Space Telescope completed one of the most accurate surveys of Cepheid variables ever done. And it was through that study that not only the age of the universe, but also the rate of expansion of the universe was determined to an accuracy and precision better than anything we had ever done before. And that was all made possible by this woman. His picture is up there. She is probably the most famous woman astronomer. At the time, she got no credit for her discovery. She was known as a computer. Maybe some of you saw the movie Hidden Figures, which talked about the role of computers even up until the 1960s, which is kind of unbelievable. But yet, there were a group of incredibly intelligent women who were crunching all the data for professional astronomers for most of the 20th century, who actually made many of the most important discoveries in astronomy, but received very little credit for them up until recently. But this woman, this computer, an amazing astronomer, Henrietta Swan Leavitt, was the one who discovered the relationship between the rate of pulsation of Cepheid variable stars and how intrinsically bright they are, the period luminosity relationship, which was really kind of the Rosetta Stone in figuring out distances in the universe. Without that discovery, we couldn't have figured out the distances to other galaxies. Edwin Hubble never would have been able to make his discovery of galaxies lying out of the Milky Way without knowledge of Cepheid variables. We'll talk about the other two methods, Type 1a supernovae, in a little bit, but also very important in figuring out the age of the universe and how fast it's expanding. So this is another picture of a quasar. This is a real picture, actually. And up until the Hubble Space Telescope, it really wasn't understood what quasars were and what type of other objects they were related to. Using data from the Hubble Space Telescope, it was realized that quasars are actually part of very, very large, very, very old galaxies that have gigantic black holes in the center of them. And from these quasars, these incredible jets of energy seen here in X-rays, very far down the electromagnetic spectrum, are always being protruded from the quasars. And so through this research, several discoveries about black holes were made. The first were that they are ubiquitous. There seems to be a supermassive black hole in the center of every major spiral galaxy that we look at. And that just wasn't known before the Hubble Space Telescope. Secondly, that those supermassive black holes seem to have a relationship with the mass of the galaxies that they're found in. It seems like the mass of supermassive black holes and the galaxies are proportional, so that if you looked at two different galaxies, one twice as big as the other, the galaxy that's twice as massive will likely have a black hole in the center of it that's twice as massive as in the smaller galaxy. So yeah, incredible stuff about black holes. We also learned a ton about solar system, or rather planetary system formation. Before the Hubble Space Telescope, there was really just theory that the planetary systems probably formed from these things known as accretion disks, and astronomers thought that there could happen 2 or 3 different ways. With data from the Hubble Space Telescope, that was confirmed for the first time. We've actually seen planetary accretion disks around other stars. We've actually seen these huge pancake-shaped fields of debris around stars that are just forming, and which will probably give birth to planets in the next few billion years. So not only were these accretion disks identified, but the specifics of how large grains of material and small grains of material move through them was also determined using data from the Hubble Space Telescope. And so that really confirmed long-standing theories about how other planetary systems around other stars take form. Another amazing discovery and huge accomplishment was the identification of both water and methane on an exosolar planet. Neither of those compounds had been observed before data from the Hubble Space Telescope. And we've now seen almost a dozen exosolar planets with water and other chemical compounds on them, which lends itself to the search for extraterrestrial life. You can find organic compounds in the same places you can find water, there's a great possibility that there might be life on those worlds. On this one, the very first planet where both water and methane were formed, life is probably not possible. This is another one of these hot Jupiters, surface temperature at about 1700 degrees Fahrenheit, probably not hospitable. But this one was close. This one was only about 63 light years away. And so I mentioned type 1a supernovae before, and their importance for distance measurements. So back in 1998, basically the rug got pulled out from under astronomers all over the world. When data from the Hubble Space Telescope and other telescopes revealed that the universe was not actually coasting at a steady rate, nor was it slowing down to eventually collapse in the future. The data from '98 and all subsequent data have shown that the expansion is actually accelerating. And those results came from the study of type 1a supernovae. So this is one star that's exploding in this galaxy. And you can see that the brightness of that one explosion almost rivals the brightness of the entire galaxy. So these are big, bright events. And just like Cepheid variables, they can be used as standard candles, as distance markers. And the reason they can be used like that is because they all explode with the same brightness. The story behind that is about the fact that when one of these stars explode, it explodes with the same amount of mass, always. How does it always explode with the same amount of mass? Well, it has a binary companion that it's sharing material with. With type 1a supernovae, you have a binary system, two stars. One star is a very, very old star, a white dwarf star. The other star will probably be a little bit younger. And one star, the white dwarf, will be sucking material from the other star, getting denser and denser, more and more massive, until it reaches a certain point. When it gets to about 1.44 solar masses, in a much smaller size than the sun, so much greater density, it collapses under its own gravitational force. And for mechanisms that are not totally agreed upon or understood, somehow there is a rebound as it's collapsing inwards, and it explodes outwards. And because it has the same mass every time it explodes, it's the same brightness every time it explodes. So just like with those Cepheid variables, all you have to do is look out to galaxies all over the universe, find a type 1a supernovae, you look at the spectra, and it has a very characteristic spectra. You look at how bright it appears, and then you can compare how bright it appears to how bright you know it actually is, and you can get a distance for that object. So through type 1a supernovae studies, the Hubble Space Telescope and other telescopes were able to prove that the expansion of the universe is actually accelerating, which doesn't make any sense. But that led to the proposal, or discovery, however way you like to slice it, of dark energy. This force that somehow fills space, pushes against gravity, and is moving all galaxies away from other galaxies, with the exception of small groups of galaxies that are gravitationally bound. But what the current thinking is now is that the universe will expand forever, faster and faster, until billions of years from now, we'll look up into the night sky, and astronomers will only see the galaxies that we're gravitationally bound to. The rest of the sky will be devoid of galaxies. And so, even though we don't seem to occupy any special place in the universe, we may actually be existing in a really special time where we can see both the large gravitational effects in the universe and that of dark energy. And so, really the whole science of dark energy started with observations made with the Hubble Space Telescope. And then, I think just the sheer beauty of the images from the Hubble Space Telescope have done a lot to just change not only astronomers' perspectives of the night sky, but really of humanity's. What we've seen in the universe since Hubble has just totally changed what we even can imagine the universe contains. And this is one of my favorites. This is the core of what's called the Crab Nebula. The Crab Nebula is a leftover gas cloud, also a supernovae remnant, that exploded in the year 1054 AD. It was called the Guest Star, observed by the Chinese, the Anasazi, several other groups. But what we're seeing here is just the inner core of that nebulae. And hidden behind the gas there is what's called a neutron star. It's a star that the core of a dead star that's become so dense that about a teaspoon of it would weigh several thousand tons. It's the densest stuff you can get before the core of a star would collapse into a black hole. And so there's this neutron star spinning a couple hundred times a second, and it can spin that fast without breaking apart because of how dense it is. And as it spins, it's giving off these pulses of energy that are radiating through this cloud of gas. And you can see some of the pulses here, these kind of spherical or circular lines that are being propelled through the nebula, kind of like waves in an ocean. And so if you go to the Hubble Heritage Archive, you can see a couple hundred amazing images like this that I think have done a lot to change the way we see the universe. Okay, so we'll get back to the Hubble Space Telescope at the end. But I want to show you 4 other really cool telescopes that are either already built and have just come online, or that will come online in the next few years. And they are going to do the same thing for astronomy that the Hubble Space Telescope has done. So the first is this behemoth, the 500 meter telescope. It's a radio telescope down in China. And its size and construction allows it to see twice as much sky as the Arecibo telescope, which was the largest radio telescope in the world before this one. This one only cost about $120 million to build, which is pretty cheap for a telescope that big. The only problem is about 9,000 people had to get relocated for it to get built. And it has 3 goals. The first is to make observations of weak gravitational waves, to make observations of the very early universe, potentially even of first light, 300,000 years after the Big Bang, when the first light separated from matter in the universe. And also, like Arecibo has been used, to make contact with intelligent life forms out there in the universe. And so, yeah, we'll see what happens with this one over the next few years.
Operational?
It is operational, not to its fullest extent, but yeah, it is being used.
What frequencies is it?
I have that in my notes. I'll get back to you on that. But it's radio, and I think it can do micro as well. Yeah. So the next incredible telescope that's coming online soon is the James Webb Space Telescope. And so this telescope has a mirror made up of these different segments that are all attached together that are gold plated. And the gold plating on them allows it to be very, very sensitive in the infrared. And so that will allow it to see even farther than the Hubble Space Telescope. It's also quite a bit bigger. The whole diameter of the mirror there is about 21 feet. And so it's got 7 times the light collecting power as the Hubble Space Telescope. So this is going to be an incredible instrument. It'll be launched in October of 2018. And unlike the Hubble Space Telescope, it's not going to be in low Earth orbit. It's actually going to be launched out several million miles away to a Lagrange point. It's going to be at Lagrange point 2. So Lagrange points are spots in space where the gravitational pull of the sun, the moon, and the Earth is balanced by the centrifugal force felt on a third object. And so they're basically like stable parking spaces for objects. We actually have a space telescope out there now, the WMAP spacecraft, but it will be replaced by the James Webb Space Telescope in just about 10 months. That's pretty exciting. The James Webb Space Telescope will likely take the first pictures of planets orbiting around other stars. It will likely solve some of the mysteries of dark energy, what dark energy is. And it may also have the potential of seeing first light, the very first light that separated from matter about 300,000 years after the Big Bang. This is the large Synoptic survey telescope. The telescope itself is not that fantastic. It's an 8.4 meter telescope, which is not the biggest in the world. There are a couple 10-meter telescopes currently up on the top of Mauna Kea in Hawaii. What makes this telescope extraordinary is the camera that's going to be attached to it. So the camera that's going to be attached to this telescope is the biggest digital camera ever made. As you can see, it's roughly the size of a small car. And the detector in this camera, the charge coupled device, the chip, is going to be able to photograph the entire night sky every week. So if you remember back to that number about the Hubble Space Telescope, the data that it collects per year, 10 terabytes per year is what's being produced right now with the Hubble Space Telescope. This camera is going to produce 12 terabytes per week. So there are whole new data management and data processing systems being developed just to analyze the data from this instrument. It can't be done manually. It's impossible. There's way too much data. And so all new algorithms have to be developed just to sift through the colossal amounts of data that this telescope is going to be producing. Yeah?
How many pixel elements are in that?
That's a great question. I can't remember the number off the top of my head. The individual...
Is it a segment?
Yeah, I can't remember the number. We can talk after and I can give you all those numbers. But the actual size of the picture that this camera takes is about 6 full moons across, with better resolution than anything ever produced before. So the idea with this is to create a 3D model of the entire universe, the visible universe. So it will actually be like a 3D database that astronomers can literally zoom through to see objects everywhere. So it's an amazing undertaking. And lastly, there's the 30-meter telescope, which recently got approved for construction on the summit of Mauna Kea. There was quite a bit of controversy about it because it's being built on what the native Hawaiianers think of as sacred land. And so there were quite a few concessions that had to be made about removing old telescopes off the mountain to get this new one built. But it will be by far the largest optical telescope in existence, with a mirror about 100 feet across. It will be orders of magnitude more powerful than the James Webb Telescope and everything else. that's in existence. This one will almost certainly see first light. The light that first separated from matter after the Big Bang. It will probably unravel a lot of the mysteries about dark matter, as well as galaxy formation and the large-scale structure of galaxies across the universe.
Is
Yeah.
it a single mirror or all?
No, it's segmented. Yeah, I can't remember the exact number of segmented pieces. Yeah, they're hexagonal mirrors. Each one of them is equipped with what's called adaptive optics. So each piece moves independently, and so it can correct for any atmospheric disturbance. So even though it's on the ground, its resolving power, like I said, will be an order of magnitude above the Hubble Space Telescopes, which is outside of the atmosphere. So adaptive optics is really what makes big ground-based telescopes like this possible. Otherwise, it wouldn't make sense to build something this big beneath the atmosphere. Yeah.
So how will they monitor the atmosphere to dial into the adaptation to correct for atmospheric distortion?
That's a great question. I don't know how they actually do that.
It's being done now.
Lasers?
Oh yeah, there are adaptive optic telescopes. Both the Keck telescopes are adaptive optics, and several others are as well. So it's still cutting edge technology, but definitely in use today. So this one is going to be incredible.
It'll be more than
Yeah,
the $100 million Chinese budget.
this one is going to be a little bit more than that.
How
Yeah.
much is this going to cost?
I can't remember the figure right now, but I have it written down in my notes. I'll tell you afterwards.
Who finances it?
There are several different universities all collaborating on this project. And I think it's scheduled to be operational in...
Universities don't have that kind of capital. Who's financing it ultimately?
Right. No, it's not government. It's privately funded. Yeah. Mhm. Yeah, it's privately funded. Yeah. I mean, there may be... I think there is some collaboration, obviously, with NASA, but that's not where the money's coming from. And I think this is scheduled to come online in either 2021, 2024. So not too far off. So I want to end with this picture of Edwin Hubble on the 100-inch Palomar telescope at Mount Wilson, which he manually moved with pulleys and gears to keep objects centered in the field of view as he took, hour-long exposures of what became, to be known as the first galaxies outside of the Milky Way. And just 70 years after that, the Hubble Space Telescope was launched. So an incredible amount of development in those 70 years. And what we're going to see in the next decade with these new telescopes that are coming online is just going to completely blow away what the Hubble Space Telescope has been able to do in the past couple decades. Some of the discoveries will probably include a confirmed observation of life on another planet outside our solar system, almost certainly. Not of intelligent life, but confirmation of biological life. It will probably include deep understanding of what dark energy is and why it exists in the universe. We'll probably learn a lot about black holes and why they exist. But all of that is still several years away. But whatever happens, I am pretty excited about what's coming down the pipe. So thanks so much for your great questions, and I'm happy to take any more. Yeah.
Colors generated on the pictures, what are they referencing?
Right.
Is there some schema on those colors that are mentioned?
Yeah, so the images that are taken in near infrared and ultraviolet, the colors are computer generated. And the Hubble has a specific palette called the Hubble palette that they use. And Mike Adler really should be the person talking about this, not me, because he uses the Hubble palette in a lot of the pictures that he develops. I think The Hubble palette, I think hydrogen is green, oxygen is blue, maybe nitrogen, I can't remember. But yeah, specific chemical elements identified with spectrographs are color-coded digitally. Yeah, there are a lot of visible light images taken with the 2 cameras on the Hubble Space Telescope, but a lot of the images you see are digital. Yeah. Yeah.
So, last couple weeks, Kepler has been had a lot of AI applied to Kepler data and what do you see happening applying AI technology?
You might repeat your question because I don't think we can hear it.
Sure. So the question was about applying AI technology to analyze the Hubble archive. Humans can only find so much in a data archive, really with the limitations of knowing what to look for. But if you can create an algorithm to look for, any anomaly, then maybe you discover stuff that you just couldn't even possibly have imagined. And that's the idea with this, this big data kind of epoch that we're moving into. That what we're going to find digitally sifting through these archives is far more than any human could have possibly discovered themselves. So I don't know, but there's clearly a lot that still can be discovered with the Hubble data. We're going to be mining just that data for decades. And as those algorithms get better and better, we'll learn more and more from that data. Yeah, great question. I wish I had a better answer, but I don't know if anybody knows the answer to that question. Yeah.
Have any of these pictures or scans ever been used with VR?
With what?
VR, virtual reality.
Oh, great question. I'm sure they have been.
Wouldn't that be fun?
Yeah. Yeah. I don't know of any off the top of my head, but I would be shocked if somebody hasn't done that. That would be cool, right? With this new 3D model of the universe that the Large Synoptic Telescope is going to be producing, you should bet that there'll be a VR of that. That's going to be cool. Yeah.
What is the period of the variable stars you're talking about? Is it days, weeks, months?
The Cepheid variables?
Yeah.
Yeah, I think it's on the order of, no. I think it's actually months. I think some of them are pretty quick. Some of them might even be days, actually.
You collect a lot of data in a short period of time.
Yeah. Yeah. I mean, and there are some variable stars that are hours. For my thesis in college, I studied the prototype contact binary system. 2 stars that actually orbit so close to each other they share material. And they had an 8-hour orbital period. So I was able to stay up all night and actually see the full sinusoidal curve of the light
And you
signature.
talked about the rotational speed of a neutron star and things
Yeah.
like that, because it's so small and so dense and
Right.
such a high angular momentum, it's going really fast.
Yep. Yeah, I don't know of any more typical pulsating stars that orbit that spin that fast. I think it's just neutron stars and magnetars.
Can I continue?
Sure.
Pulsars, when you have anything, whether it's a star or a black hole or whatever it is that's generating jets coming out, bilateral,
Yeah.
symmetrical jets, the source, I understand, is the accretion material going in and collapsing and spiraling in.
Well, it's not actually falling in past the event horizon, but it's spiraling into the black hole, giving off a huge amount of energy, and then some mechanism shoots it out as a jet. I don't think anybody knows how the jet actually forms, but that's where the material is probably coming from.
There's a magnetic field involved.
Right. But how it actually works, I don't think anybody knows. But yeah, a pretty strong magnetic field.
If the universe is expanding at an accelerating rate,
Right.
and the cause of this is dark energy,
Yep.
sounds like you've got to have dark energies created more and more.
Yeah, so it's really strange, to say the least. So the universe is getting bigger, space is getting bigger, and where is that all coming from?
Yeah.
The 4th dimension. Yeah, so I mean, this is really there are kind of 2 competing theories. One is that that space really is this matrix that everything moves through, and that there really is more of it being born out of a fourth dimension. We don't really understand why that can exist. Einstein actually was the first to propose that. He thought of the universe as what's called a three-sphere. A three-sphere, you kind of think of it like this. So our experience on Earth is that it's a two-dimensional surface. We walk forward and backward, left and right. But we know that if we take a step back and look, it's actually a curved surface. It's a two-dimensional surface wrapped around the third dimension. So that if you walked in one direction, you would eventually end up where you started. Well, Einstein proposed that the universe is exactly the same. That if you flew in one direction from Earth out to the universe, you would eventually return to Earth, traveling in a straight line the whole time. So that's the fourth dimension.
What's the other?
The other theory, yeah, right? The other theory is not much better. The other theory is real cutting edge. This gets into what's called quantum gravity. So this theory is that space is not a substrate that the universe actually, that the stuff in the universe moves through at all. That space is actually stuff as well, and that it's granular, just like any matter is granular. And where that comes from, I don't think has actually been developed as part of that theory yet.
Two black boxes.
Yeah, two black boxes, but all the data, all the theoretical data from quantum mechanics seems to be suggesting that space really is granular, and that it's just a field, just like the gravitational field or electromagnetic field. We just perceive it differently because of our limited consciousness, which is really strange. It means that there's nothing that galaxies are moving through, that they're just interacting with this other stuff that we just happen to call space. That one is yet to be determined as well. Any other, if you want to know more about that, there's a brilliant book out about it right now called Reality is Not What It Seems by Carlo Rovelli. Absolutely masterful. He goes through all of the history of astronomy from ancient Greece up through quantum mechanics, and it weaves it all together just in an incredible way. It'll blow your mind. Reality is Not What It Seems. Carlo Rovelli. Really, really good. Any other questions?
If there are no more questions, and Sam will be here for a
Yeah.
minute or so afterwards.
Well, can I make one shameless plug before I end? Shameless plug is that Mike Adler was good enough to give us a bunch of his images from the eclipse, and we put together a 2018 Eclipse Calendar. We're selling them through the Wyoming Stargazing website. So if you want to come take a look at it, I've got one up here. That's my shameless plug.
So, good news tonight. The chairs get to stay where they are until January.
No, just for tomorrow morning.
Okay. All right, just for tomorrow morning.
Figure it in, so don't worry.
But I want to take this opportunity to thank Sam for yet another incredible talk. You are such a passionate speaker.
Oh,
Please
thanks.
accept this.